Hello and welcome to this introductory tutorial on 4D-STEM with the Ceta camera and the Electron Microscope pixel array detector, aka the EMPAD. In this first section on phase mapping, we'll be covering how to go about setting the optics for 4D-STEM, how to use virtual detectors with the Ceta camera and Velox, how to acquire 4D-STEM datasets simultaneously with EDS, and then we'll take it to the next level with the EMPAD, where I'll cover the user interface and how to acquire high-quality datasets with extremely high dynamic range at more than 1,000 frames per second. Before we dive into it, I want to give you a brief overview of the sample we're using and the goals for our experiments. For our phase mapping component, we're using a commercial 718 nickel-based superalloy material, which has gone through an additive manufacturing process where secondary phases are formed during cooling. These coherent disc-shaped precipitates have a clear orientation relationship with the matrix, forming three distinct variants orthogonal to each other. If we change our perspective to look down the 001 axis, you can get an idea of what morphology we would expect if we prepared a TEM sample in the same orientation. So we expect to see all three variants present throughout a sample. But because they're coherent, they impart strain fields on the matrix, which result in a lot of diffraction contrast, making them hard to see clearly. This is where 4D-STEM can be really handy, as we're acquiring a diffraction pattern for every probe position in a STEM image, and we can use those patterns to isolate single variant types using virtual detectors. And that same data allows us to do more advanced processing, like visualizing their strain fields, for example. So let's get started and open the column valves. We're using a Thermo Scientific Talos F200X G2 TEM today, and the software and setup will be very similar on Spectra-type instruments as well. Here we can see a reasonably thin section of our sample, where the niobium-rich precipitates show up brighter due to Z contrast, and you can start to make out the two sets of edge-on variants. Let's insert our SmartCam, which is the fluorescent screen. Here you can see the transmitted beam and the diffracted disks within the hull of the HADF detector. Here we're using fairly standard high-res STEM settings with a 10.5 milliradian convergence angle and 100 picoamps of probe current. It's important that we verify our ROI is close to the zone axis using stage tilt if necessary. You'll notice there's quite a bit of overlap between the disks, which is not ideal for this type of phase mapping where we want to isolate superlattice reflections. We need to reduce our convergence angle to achieve a more parallel beam, which will make the spots smaller in our diffraction pattern. To do this, we'd use a smaller C2 aperture, like a 50 or a 20 micron, and also switch our optics from nanoprobe to microprobe mode. On Spectra, we can change our C2-C3 ratio for added control. The best way to change modes is to load a FEG register, but if you don't have one, it's simple to make one, provided the microprobe stem column alignments have been performed on your system. One nice trick with a SmartCam is that we can overlay a reference circle to verify alignment of other apertures in diffraction mode. This is particularly handy for very small C2 apertures. Here we can drop to a 50 micron aperture, and you'll notice the spot overlap is reduced, and we're now at a 7.5 milliradian convergence angle. By changing our optics to microprobe, we can jump all the way down to 1.5 milliradians. If we use a 20 C2, this would be down to about 0.6 milliradians. You can see the transmitted beam is now much smaller in size, and the next steps would be to exit diffraction and run through the direct alignments. To save time, we're going to start fresh and load a FEG register. This sets up the full column for our experiment type. Because we have constant power lenses, these alignments are stable and reproducible, and we don't get drift when jumping back and forth between optical modes. Here we insert the HADF detector and mag up to the same ROI. We're using a frame size of 256 by 256 and a dwell time of 4 microseconds. We're using the same 205mm camera length as before, but now we have a 1.5 milliradian convergence angle, as we've changed from nanoprobe to microprobe mode. We can verify this under the optics dropdown. Let's go ahead and insert the SmartCam again, which is our fluorescent screen. And you can see the spots are now much smaller than before. We can even start to see some of the superlattice reflections, but these will show up much better on the Ceta. So let's get ready to start our 4D-STEM experiment. We'll stop the scan, pause the SmartCam, and lift the screen. We can ensure that the Ceta is inserted by checking up here in the Detectors dropdown. Under the settings for the Ceta, our 4K CMOS camera, we're going to start out using an 8th readout, which will allow us to work much more quickly, with just a 5 millisecond exposure time. We'll disable the shutter during imaging and verify dark and gain corrections are enabled. We only need to set up the search tab, as it uses the last active preset. Let's hit search, and we can see that we have a nice view of the first order Bragg spots. If we move our probe around on the sample, we can park it on a precipitate where the superlattice reflections really shine. Although we can use our Hadaf detector, let's retract it and use virtual detectors instead. These superlattice spots correspond to one of the 3 precipitate variants. We'll first pause the camera readout and blank the beam. By scrolling to the bottom of the right side, we can see we have the option to add up to 8 virtual detectors, which can be rings or disks. The parameters are X and Y position for the center, and inner and outer radius in milliradians. For a disk detector, we would set the inner radius to 0. I'm enabling some virtual detectors for the bright field disk and one for each set of precipitate variants. And it's always a good idea to periodically use a line diffraction shift to ensure your center spot is in fact centered. Next, let's check our spectrum imaging settings. Right now we have a 5 millisecond dwell time, which should match the Ceta camera exposure time. We can confirm that we're connected to our Ceta server, which is required for high-speed data offloading, and we have simultaneous SuperXEDS enabled. Let's insert the Hadaf detector again before we start our acquisition, since the full STEM scan area is much more than we need. We'll refresh the image and then select a more targeted ROI, which we'll set to 100 by 100 pixels. This should give us 10,000 diffraction patterns per acquisition, which will take a little under a minute to acquire. Let's retract the Hadaf again, confirm our experiment duration, and then hit the Acquire button. In the Velox acquisition window, we'll get a live view of all the real and virtual STEM detectors that are active for our experiment. Here we can start to see the bright field image in Virtual Detector 1, which has a whole lot of competing contrast mechanisms at play. Alongside it, we can already see the 3 precipitate variants being separated out as expected in the Virtual Detectors 2, 3, and 4. Let's jump to the Velox processing window, where we can see the same virtual STEM images as well as some EDS spectrum images. We can work with the virtual STEM phase maps in the same way we work with EDS maps, and can change the colors if you like. Velox allows live EDS quantification during acquisition, so we can activate net intensity mode, which applies background correction and peak deconvolution to the spectral data from each of the 4 detectors. This really enhances the elemental maps for titanium and niobium in the sample, and we can further improve quantification through absorption correction and pre-filtering once the acquisition is complete. Now that it's all done, let's open up the stack of diffraction patterns that get saved to the Ceta high-speed server. As expected, there are 10,000 16-bit frames in this MRC file, which you can open in just about any image processing software like ImageJ. You can export some reference frames from Velox, or even a movie if you wanted to show the raw data in a presentation, for example. Let's continue and move on to using the EMPAD in similar conditions. Before we launch the EMPAD user interface, let's first retract the Ceta camera, since they share the same position in the microscope column. The TEM does have anti-collision functionality built into the software, which prevents them both being inserted at the same time. We can open up No Machine, which is our portal to the EMPAD PC, which is running Ubuntu, and launch the EMPAD UI. We can then start by clicking New and entering a name for our project before clicking OK. This reveals the Connections dialog box where we'll select Go Online. Once the cam server, microscope, and detector control unit all give the green light, we are launched into the full user interface. Here we'll start by clicking Power On and giving it a minute to initialize. Next, we can go ahead and insert the EMPAD. Once inserted, the EMPAD will begin cooling the sensor to -5 degrees Celsius, which will take a few minutes. In this video, we'll jump ahead to save time. Now that the sensor temperature is stable, we need to acquire a background image. Make sure the beam is blanked or the screen is down for this. Clicking the Video On button gives us a camera readout where we can confirm we have a dark, flat image. Next, let's jump back to Velox to optimize our settings for the EMPAD. Here you can see on the SmartCam we were using a relatively low camera length of 205mm in combination with a small camera readout area on the Ceta. With the EMPAD, we're using the full sensor, so we need to increase the camera length quite a bit. In this case, I'll go for 660mm to get a similar field of view in diffraction space. I'll stop the scan, retract the Hadaf detector, and move the probe around a bit to confirm I'm still reasonably close to the zone axis. I'll pause and hide the SmartCam, and then lift the screen, ensuring nothing is blocking the beam path. Then I need to hand control of the scan coils over to the EMPAD, which on Talos is done in the software by finding the STEM imaging dialog box, opening the flap out, and changing scan input from internal to external gen. On some of our microscopes, you would do this using a physical switch box. So back to the EMPAD UI, let's hit video on again and we see our diffraction pattern shows up nicely. I'll enable the cross to find the center, and then use Align Diffraction Shift in the direct alignments to ensure my pattern is nicely centered using the multifunction knobs on the microscope hand panels. The EMPAD UI also has virtual apertures which you can set up in a similar way to how we did it in Velox. Here I'm loading a preset that's similar to what we had before. There's also a segmented annular virtual detector for doing differential phase contrast measurements. Next, let's check our scan settings. We're using a 64 by 64 pixel search preset and 128 pixels for acquire. With our search preset enabled, I'll click Focus On, which will give us a live view from one of our virtual detectors. In this case, it's showing us only the vertically aligned precipitate variants in the field of view, which all share a superlattice reflection in the diffraction pattern. I'll increase magnification to get a better field of view, and can change the view mode to my summed annular detector. Now I get a virtual ADF STEM image which provides a bit more context. A key advantage of the EMPAD over the Ceta is its extremely high dynamic range. It can detect a single electron in one pixel and a million in an adjacent pixel without saturating. And that's a huge advantage, as most other direct electron detectors saturate very easily and can damage easily, unlike the EMPAD. Some 4D-STEM experiments do need more pixels, however, and that's where the Ceta has an advantage. So let me switch to the Acquire preset and click Take to get a complete dataset here. We're using a 1 millisecond dwell time, but we can go a little bit faster than that to 1100 frames per second, which is quite a bit faster than the Ceta. I'll speed this up a bit, and once it's done, it'll ask me to choose a name for this acquisition. And then I can flip through our virtual detectors where we can see very clean separation of the variants. What I've shown so far has been a very basic use case, but a sample like this really makes it easy for beginners to understand what's happening and see the results live. In the next parts, we'll show you how to set up some more advanced 4D-STEM experiment types on different samples, and you'll gain a deeper understanding of how to maximize the performance of your microscope setup for your experiments.
Welcome to our tutorial on strand mapping experiment setup. Today we'll walk you through the essential steps to set up the experiment and acquire the data. In this experiment, we're going to use a silicon-silicon germanium superlattice sample. In addition, we're going to use microprobe mode to avoid overlapping between the bright disks, and with a screen current of about 100 picoamp. To start, I load a pre-made FAC register, and this helps me set the convergence angle to about 0.6 milliradian. For more details, please watch the orientation mapping video. The next thing I want to do is to put in the Ceta camera, choose a proper camera lens, and center my diffraction pattern. First, I used 1/8 readout that uses the very center of the detector, and this helps me read out much more quickly. After I set the exposure to 5 milliseconds, I can start adjusting the camera lens. Here, I use a camera lens of 160 mm as it gives me more back reflections on my detector. After this, I need to center the bright disk with respect to the detector. I can bring out a crosshair, which indicates the center of the detector. Then I move the probe around to identify the center beam, and center the diffraction pattern on the detector. Once I'm happy with the setup, I switch back to head-off and try to change magnification for a good field of view. Then I selected 256 by 256 scans, which sets the pixel size at given magnification. With the toolbox, I can select the region of interest and define the size of the scans. Once I'm happy with that, I can take out head-off detector and make sure that the spectral exposure matches with the Ceta exposure. Now I can go back to Ceta to view the diffraction pattern and set up virtual detectors. Setting up the virtual detectors allows me to scan without head-F, and therefore I can take out the head-F and avoid shadowing. I set up a virtual bright field and a dark field detector. With that, I can start my acquisition by simply hitting the SI Acquire button. Now we'll wait for the acquisition to be done. Data will be saved automatically. It should be noted that the 4D-STEM data is going to be saved on a different folder with respect to the project directory. It is going to be saved in the offload data folder, and it will be saved as an MRC file. For more details on how to viewing the data in ImageJ, please refer to the orientation mapping video. Thank you very much for joining us on this tutorial on 4D-STEM data acquisition for string mapping. Stay tuned for more videos. Welcome to our tutorial on Center of Mass 4D-STEM data acquisition. Today we'll explore not only the experiment setup and acquisition process, but also the fundamentals and applications of this advanced microscopy technique. Before we start, I would like to give a brief overview about the sample. This is gallium arsenide, aluminum gallium arsenide semiconductor sample. N-type and P-type doping can create two-dimensional electron gas as shown in the figure. In this tutorial video, we're using gallium arsenide, aluminum gallium arsenide, and indium gallium arsenide, where we have both N-type and P-type. The center of mass method within 4D-STEM focuses on calculating the center of intensity for each diffraction pattern, which allows to map the electromagnetic fields within materials. For this method, the choice of camera lens and convergence angle is critical, since it defines the size of the diffraction pattern to be computed. The COM experiment utilizes a similar alignment with standard STEM imaging. For this example, we set the convergence angle to 10 milliradian, which is the optimum convergence angle for talos. With spectra, there is more flexibility in changing the convergence angle. The screen current was approximately 100 picoamp over vacuum, and we selected a camera lens of about 205 mm. This allows us to collect about 70% of the intensity of the diffraction pattern, which is enough for the center of mass analysis. Now let's start setting up the experiment. First, we move to the region of interest, magnify, and fine-tune focus and astigmatism at atomic resolution. Here we're at gallium arsenide, aluminum gallium arsenide region. Once everything is perfectly aligned, we switch magnification to select our desired field of view. After we blink the beam and switch to EMPAD, we want to take a background reading and video on to double-check the background correction. After this, we hand over the scan control to EMPAD. At your system, this can be a physical switch button. Remove head-F and the screen, and revert to EMPAD GUI. With the video on, we view the diffraction pattern, adjusting the display exposure for better visibility. We then align the diffraction pattern at the center of the detector. After the alignment, we start with a 64 by 64 scan for the search mode for the overview. Search mode allows you to quickly preview your region of interest. It lets you view a calculated image of your chosen settings in Rankine mode. However, you might notice that the image appears quite pixelated. We switch to a 128 by 128 scan, capturing a higher quality dataset on the same region for acquisition. I want to point out we're using an exposure of 1 millisecond, but we have the ability to go down to 0.1 millisecond. Here we used EMPAD for this experiment because it captures diffraction pattern at every scan point. This extensive data opens up a range of post-processing opportunities. For example, generate images with virtual detectors. Once the acquisition is done, we simply hit OK and the data is saved automatically in the project directory, together with an XML file containing its experiment conditions. The EMPAD GUI also allows us to set different diffraction phase contrast detectors, including the directional and some options. Thank you for joining us for this tutorial on 4D-STEM data acquisition using the center of mass method. You can watch more information about how we optimize detector and camera parameter in the orientation mapping video. Welcome to our tutorial on 4D-STEM ptychography data acquisition. Today we'll walk you through the essential steps of setting up and running an experiment, focusing on a single-layer tungsten diselenide sample. For the ptychography experiment, we use quite similar conditions for standard STEM acquisition, with a screen current of about 20 picoam over vacuum and a convergence angle of 10.5 milliradian. We choose those conditions following the Illinois group's paper, where Talos was used for the experiment, with a link attached below. The alignment is the same with STEM imaging to achieve optimum conditions where CS aberration is the main constraint. You have more flexibility as spectra and increase convergence angle easily with the corrected system. To start the experiment, let's load the factory settings which I have already prepared. These settings adjust the beam current to about 20 picoamps and ensures minimal damage to our sensitive material. If you're starting without a predefined settings, adjusting screen current can be easily managed by modifying spot size or gun length. After setting the screen current, our next step is to check the camera length to determine the maximum collected K-vector. To do this, I'll place a probe over vacuum area and use a bright disk on the detector to estimate the maximum K-vector. So remove HDF and the screen and switch to EMPAD so that I can view the bright disk on the detector. Then change camera lens based on the bright disk. For this experiment, we choose a 98mm camera lens, allowing us to collect a K-vector approximately 8 times the size of central bright disk, equating to about 3.9 inverse angstrom and corresponding to a real space pixel size of about 30 picometer. Next, insert screen and HDF back in. We then move to a region with visible contrast and attempt to bring the sample into close focus. After adjusting the height, I can use the built-in function to correct any astigmatism and fine-tune focus. This automatic function is highly effective, usually bringing the system into nearly perfect focus. Once the focus and astigmatism are adjusted, typical ptychography experiment uses either over or under focus conditions for more probe overlapping. In this experiment, we used in-focus condition to stay consistent with the paper. Now let's shift the stage to our region of interest. Here I use piezo controls for the X and Y axis for more precise stage movements and fine-tune the imaging conditions. When satisfied with the setup, we begin the data acquisition. Now let's hand over the scan control to EMPAD. Remove the screen and HDF, and revert to EMPAD GUI. Here we use an exposure of 1 millisecond. X and Y scan dimensions were set to 128 by 128 pixels, with a 20mx magnification, resulting in a scan step of approximately 0.53 angstrom. For ptychography, capturing detailed diffraction patterns is critical. For this purpose, we require a camera with high dynamic range, linear response, and high-speed capability. These features ensure that we can accurately measure the intensity, which is essential for reconstruction. Therefore, we use EMPAD rather than the conventional CMOS detector. And after the data collection completes, simply hit OK to save the data. The data will be automatically saved in the project directory. Thank you for joining this tutorial. We hope those instructions will assist you in conducting your own 4D-STEM ptychography experiments. For more information, please watch the theoretical video about the reconstruction methods within 4D-STEM by Professor Chen.